Hello everyone, I remain your tutor Mr. Life Changer. In this video I'm continuing on the series MCQ on isomerism. In the previous video we saw questions on chain isomerism and positional isomerism, and here we are going to continue. Hopefully we see the rest in this video. So here we look at functional group isomerism. Now, functional group isomers have different functional groups. Their functional groups are different, and there are some organic compounds that are isomers with some other organic compounds, and there are many of them. You know, things like alkanols, we call them alkanols, and ethers are isomers. Okay, we have alkanals. We have alkanals and alkanones are also isomers. We have alkenes and cycloalkanes. Though nobody's really going to ask you this, alkenes and cycloalkanes. Then we have carboxylic acid and esters. Okay, carboxylic acid and esters are also isomers. Okay, yeah. I forgot to also add that especially here you could also have something like epoxide, or what we call alkoxide, but that's by the way. Okay, but for now these are the major compounds that are isomers with each other, and I hope this will be helpful. Let's look at the next question here. It says study the diagram C3H6O isomers functional group isomerism have. Now the answer to this question is B. They have the same molecular formula but entirely different functional group. If you look at this now, this is a propanal, okay, and while this is propanone, they are of different functional group. So the first one is CH3, CH2, CHO. If you notice, it has 3 carbons, it has 6 hydrogens and 1 oxygen. Then propanone has CH3, CO, CH3, also has 3 carbons and 6 hydrogens and 1 oxygen. But I want to add that there is also one more isomer that is missing here, and there is also a functional isomers with this one. Like I mentioned earlier, they are called epoxides. We call them epoxides, and let's say you could have something like this: CH3, CH, CH, like this, then O. This is a very good one. This one has 4, 1, 2, 3. Okay, this should be CH2. So if you count this, you're going to have 3 carbons, 1, 2, 3. Hydrogen is 3 plus 1, 4, 4 plus 2 is 6. Then oxygen. So you can see C3H6O. That's by the way. Okay, so that leads us to the next question. It says from the diagram of C2H6O, isomers ethanol and methoxymethane are functional group isomers because A says they have different molecular formula. No, isomers have the same molecular formula. B says one is an alcohol and the other is an ether, yet both have this formula C2H6O. That's amazing. That's the correct answer to the question. C says they have the same boiling point. No, they can never have the same boiling point. In fact, ethanol has a higher boiling point than methoxymethane because of the presence of hydrogen bonding, but that's not the purpose for this class. Now, they both undergo the same chemical reaction. No, they do not. Okay, so the next question here says, which pair of compounds are functional group isomers? Remember, the idea is that they must have different functional group. And from what I can see here, the answer is C, propanal and propanone. Extremely very important. The first one is a chain isomer. You see, this one is a branch, so it's a chain isomer. The second one is a positional isomer. Here, position 1, here, position 2. This fourth one is also positional, but 1 in and but 2 in, just different positions of their functional group. Okay, so the next question here says carboxylic acid and esters with the same molecular formula are example of functional group isomers. Carboxylic acid and esters. Let me give an example. I think I should do that. Let's say, look at this, CH3COOH. Okay, this is called ethanoic acid. Okay, you know an alkanoic acid with this symbol COOH. Then esters, let me have this HCOOCH3. You know, check my previous video on naming of compounds. You're going to see where I showed you how to name this. For this one, this is methyl methanoate. That's what this is called, methyl methanoate. And if you check, you're going to see that both of them have 2 carbons, they have 4 hydrogens and 2 oxygens, and that makes a lot of sense. Okay, if you want to write the open structure for this, it's going to be like this: CHHH, then COOH, or you say C double bond O, then OH. Then for this one, it's going to be HC double bond O, then O, then CH3 HHH. This is the open form. Some persons might be interested in this. Now that leads us to the next question. It says, which of the following is a functional group isomer of CH3COOH? I already did that. I'm a genius, right? Okay, so that is that. This is a functional isomer. This is an ester, while this is an alkanoic acid. Okay, so the next question here says, alkynes and dienes compounds with 2 double bond with the same molecular formula are best classified as also their functional group. Even though you shouldn't really bother yourself with this, but you can know this. When you have this is called butane. Okay, for example, then you could have CH2 double bond CH, then CH double bond CH2. This one here is called but 1,3-diene. That's what that means. If you count it, you notice that the both of them has 4 carbons and 6 hydrogens. This is 1, 2, 3, 4, 5, 6. You see? So 4 carbons and 6 hydrogens. So butane and but 1,3-diene, that means a diene, are also isomers. Okay, that's very important. Now the next one here is the geometric isomers. Geometric isomerism is cis or trans. Okay, it's important for you to know that is a stereoisomer depending on the arrangement in space. A cis isomer, and it exists in especially alkenes for our level, but for higher level it also exists in cycloalkanes, but I'm going to be interested in just alkenes. Now look at this. This is carbon-carbon double bond, but here you have CH3 and here you have CH3. They are both on the same side. That's what makes them cis. Okay, but here you notice that carbon-carbon here, CH3 is here, CH3 is here, and that makes it trans. It is trans. That's important for you to note. Now number 19 says, study the diagram of cis and trans butene. Geometric isomers arise because A says there is free rotation about the carbon-carbon double bond. That's not true. There is no rotation there. B says there is restricted rotation about the carbon-carbon double bond, leading to a different spatial arrangement. And that is it. Because this cannot rotate, along this carbon because of the double bond, gives us that spatial arrangement. C says the 2 isomers have different molecular formula. No. D says the carbon chain can branch in different ways. No, not exactly. Okay, now this one says, from the diagram in the cis isomer of butene, the 2 CH3 groups are, of course, the answer is B. They are on the same side of the double bond. Okay, that's how you know cis. Now the next one says, which of the following compound cannot show geometric isomerism? I like this. This is very important for us to know. And now the following compounds cannot exhibit geometric isomerism. Anytime you have, let's say, carbon-carbon, and you have X here, you have X here, the same thing on one side, then it cannot. Even if you have different things here, as long as you have the same thing on one side like this on the same carbon, then it has failed the test of isomerism. I hope I am making sense. It has failed the test. Now let's draw the isomeric structures for this one. If you want to draw an isomeric structure, you start from the middle. This is CH double bond. So I say C double bond C. You have the first hydrogen here, you have the second hydrogen here, then you have CH3 here, and you have the second CH3 here. That's the open structure for this. For this one, see where the double bond is. You have C double bond C, but this C now has two hydrogens, hydrogen and hydrogen. And why this other one has a hydrogen, then now has CH2, CH3. Of course, this will definitely be the answer because this does not exhibit isomerism. Because you can see hydrogen, hydrogen on the same carbon. That would be very wrong. They need to be on adjacent for them to experience isomerism. But let's try with the other ones. Look at this one, CH, C double bond C. There's a H here, there's a H here. Then there's a Cl here, there's a Cl here. The same thing with this one. You have CH. So C double bond C. You have a H here, you have a H here. Then here you have COOH, butene dioic acid. And here you have COOH. Very beautiful. This is also exhibit isomerism. So B, option B, does not exhibit isomerism. That should be helpful. Now the next question here says, referring to the diagram of malic acid and fumaric acid, this is malic acid here, okay, this is fumaric acid here, which is a trans, this is cis. Now it says, which isomer has a higher melting point? Okay, are you there? So you should know that the isomer that has the higher boiling point is usually the trans isomer. Okay, the first one says malic acid cis, and no, B says fumaric acid trans because more symmetric structure allow closer packed in the crystal lattice, which is the answer to that question. Number 23 says, what is the minimum structural requirement for a compound to show cis-trans geometric isomerism? A says carbon-carbon single bond with restricted rotation. No, not at all. B says a carbon atom bonded to 4 different groups. No, not at all. C says a carbon-carbon double bond where each carbon carries 2 different groups. Each carbon must carry 2 different groups, which is correct. D says at least 2 chiral carbon atoms. No, not at all. So the answer is number 20. No, the answer is C. Okay. Now that leads us to the next one here. It says, which of the following is a cis isomer of 1,2-dichloroethene? A says chlorine and chlorine on the same side of the carbon-carbon bond, hydrogen and hydrogen on the other side. Okay. B says chlorine and hydrogen on the same side, chlorine and hydrogen on the other side. Actually, the answer is not A. The answer is B. Chlorine and hydrogen on the same side, then chlorine and hydrogen on the other. This one says chlorine on one carbon, no chlorine on the other carbon. No. Both chlorine atoms attached to the same carbon. No, that's not true. The answer is chlorine and hydrogen on the same side and chlorine and hydrogen on the other side. That you're going to have something like this: chlorine Cl and hydrogen on the same side, then chlorine and hydrogen on adjacent side. Can you see that? I hope that makes sense. Okay, so the answer is B to this question. That's an error. Okay, so the next one is optical isomerism. Now, to throw a little light on optical isomerism, optical isomers are mirror images to each other. Mirror, M-I-R-R-O-R. Just like we have here. This one here is a mirror to this. But the only compounds that can exhibit optical isomerism are compounds that have a central carbon and different groups attached to it. Like, look at this compound here. There is a carbon here. Here is hydrogen. Here is methyl. Here is OH. Here is COOH. This is the kind of compound that can exhibit optical isomers. And this kind of compounds are called chiral compounds. CHR, I call it chiral, you can call it chiral, whichever. Chiral compounds. And their carbon are called chiral carbon. Okay? And so that means something like this. Look at this. this cannot exhibit optical isomerism because you have 2 repeated hydrogen. There should be no repetition of group around carbon. Okay, once it does that, it means that it can to be optical simply means anything that can be influenced by light. Well, also that means an object is optical if it can be influenced by light. It can rotate in the presence of a polarized light. Okay, so let's start with the questions here. This one says, study the diagram of the optical isomers of lactic acid. Optical isomers, enantiomers, are best described as A. Compound with the same formula that differ in their position of functional group. That's not true. That's rather functional. B says compounds that are non-superimposable mirror images of each other. That is exactly what it is. They are mirror images and non-superimposable. Now, C says compounds that differ in the position of the double bond. No. D says compounds that differ with different molecular formula. No, not at all. Isomers must have the same molecular formula. You can see that makes a lot of sense. So B is the answer. Now let's see the next question here. It says from the diagram 2-bromobutane optical isomers, the chiral carbon is the one bonded to. Okay, yeah, this is 2-bromobutane. So the optical isomers, the chiral carbon is the one bonded to A. Only hydrogen. No, that's not true. B. CH3, this and this, 4 different groups. That's it. It must be 4 different groups. And you can see that this is a mirror image of this. When you flip this, when you flip it to the other side, you are going to have this. That's how it works. Okay. And the next one here says, which property differs between optical isomers? The answer is the direction in which they rotate in plane polarized light, which is not really for your level. That's an advanced question, but you should know this. They rotate in different directions. One of them rotates clockwise, the other one rotates anti-clockwise. Okay, then this one says, which of the following compound has a chiral carbon and can therefore show optical isomerism? That's interesting. Look at this one, for example. You have CH3 here. Look at this carbon here, has hydrogen. Then here has CH3. Cannot, because C repetition, hydrogen, CH3, so cannot. Look at this one here. Let's try this one, this carbon here. You have carbon having hydrogen, then here you have OH, and here you have CH3. It would not work because of hydrogen repetition. It doesn't work. Now let's look at this one. This carbon here, let's see. This carbon has hydrogen. It has OH, it has COOH, and here it has CH3. Yeah, correct. Because different groups are attached to a central carbon, a chiral carbon. I believe that makes sense. Okay, the next one is racemic mixture. Now, a racemic mixture has equal number of enantiomers. I forgot to mention that optical isomers are also called enantiomers. That's what they are called. So enantiomers are 2 compounds that their relationship is optical isomerism. Okay, so the answer, a racemic mixture has an equal mixture of 2 enantiomers that has no net rotation of plane polarized light. That's by the way. For this one, I'm not going to do this, but the answer is 2 chiral carbons. But that's not necessary for you. Thank you very much. See you in my next video. I remain your tutor, Mr. Life Changer. Don't forget to share, subscribe. This video help somebody. I know a lot of people would want to go through my classes. I do my best to make things as easy as possible for you to be able to scale through your exams, and it's also going to help those of you that are entering undergraduate. It's going to be very helpful. Thank you very much. See you in my next video.